Maya says hello. I have no idea if she was meowing to the music or not. Let me turn that down here, and we'll get started. Hi, everybody. Welcome back to Chem 121. That's what we're doing right now, right? Yeah, that's right. This is not my first class today, which is really weird. So during week 5, all the schedules kind of change. In fact, I should probably put that in the announcement down there tomorrow. So note the syllabus. Our schedule is going to be a little different this week. So we have class today. That's normal. But the second lecture this week is actually going to be tomorrow. So lecture tomorrow, Tuesday. So we'll put that down there just to remind you. Because Wednesday this week, all my classes are review sessions. So we're going to do our 2 lectures this week, Monday, Tuesday. Wednesday's a review session, so bring any questions you want. I will bring a cat. I mean, she will bring herself. I don't really have much... Why are you yowling from the bathroom? Sorry, I was talking, and then I was rudely interrupted by "Meow" from like 3 rooms away. No, I'm teaching. No, you can't. No, you cannot jump in my lap. No. You cannot jump in my lap. No. No. I'm busy. Yeah, okay. The review session is live stream. It's just like this. It's just that instead of lecture on Wednesday, it's actually on Tuesday. I don't want people to miss the Tuesday lecture. That's all. That's really all. There's a quiz due this week. It's due tomorrow, it looks like. And then lab worksheet number 2 is due Wednesday. So make sure you get those in on time. I realize that there's going to be a lot of stuff coming in. So hopefully you have done most of the lab worksheet and at least attempted quiz number 4. And if you have, then you're in great shape. If you haven't started any of that, it's going to be a rough week for one of us. Hint, it won't be me. We're going to do more Lewis structures today in Chapter 5 for covalent compounds. We're going to start drawing Lewis structures for, like, water and stuff. So you've probably already seen these types of structures already. We're going to learn how to do that in this class. So the first thing that we need to do is we need to identify when is it appropriate to draw a Lewis structure for an ionic compound versus this new style that we're going to do, covalent. And that has to do with the type of bonds that we're going to explore in this section. Now, physically, and then using our senses, we can depict the difference between these compounds in the following way. Some substances have really high melting points, like ionic compounds do, but others have really low melting points, like water. Water's melting point is freezing. It's like 32 degrees Fahrenheit, right? Water becomes a liquid at a relatively normal temperature, which is room temperature. But for these ionic compounds that we studied in the previous chapter, they're very, very, very sturdy. They do not melt until you heat them to like thousands of degrees. You also see that substances that are covalent do not have crystalline types of appearances. They're either powder-like, or they're chunky, or they're waxy. So, like, if you take candle wax, excuse me. You take candle wax, there's nothing crystalline about that. Like, it's malleable in your hands, you can stretch it apart. It's kind of goopy almost, as opposed to something like sodium chloride, which makes a very big crystal if you compact it into, say, like a salt block. I don't know if you've ever been to a farm where you had like the salt licks that you give out to cows, because they need sodium too, and so you put these like blocks of salt everywhere, and then the cattle just come by and lick them. And so that would be like a giant crystal of sodium chloride. Well, of compressed sodium chloride crystals together. So the takeaway from this discussion is that because the properties of these substances are so vastly different, the bonding in them must be... excuse me. Sorry. I slept fine. I don't know why I'm yawning all of a sudden. It's just 2 p.m., I guess. It's yawn o'clock. So the bonding in covalent compounds must be totally different than that of ionic compounds, because ionic compounds are held together extremely well, and their melting point is very high, their bond strength is high, but molecules are very different. So we're going to explore that in this chapter. Now, just like in the previous chapter, we're going to follow the same goal as before. If I start with some number of electrons, my goal is to get to an octet. But how we're going to go about doing that in this chapter is a little bit different, because instead of pairing a metal with a nonmetal, what we're going to do is we're going to pair two nonmetals together. So I'm going to just put a generic nonmetal here. And we'll do another one here. And if I transfer electrons over, this one gets further away from an octet, and this one gets closer. Well, how do I get them both to get to an octet if moving electrons makes one get further away? And the answer is, well, I can't transfer electrons. If I transfer electrons, this happens, and that's no good. We don't want that. So we need to come up with a different idea. And what we do instead is we share electrons. So what we would do is we would say, okay, I'm going to take all these electrons here, and we're going to share them. I need 2, you need 2, I'm going to borrow your 2, and you're going to borrow my 2. We're going to just share them at the same time. And that will resolve this issue. Everything will have an octet. Alright. Any compounds that share electrons are going to be called covalent compounds. Now, the bonding that arises from covalent compounds will be different than ionic compounds. Ionic compounds created charges, and those charges went in every direction. But covalent compounds form bonds that only go between two atoms. They don't attract to other molecules. This is why they're molecular. They are independent units because the atoms are bonded in a certain geometry. All right. The only electrons that can be shared between atoms are unpaired electrons. So here's how this works. I'm going to put 2 fluorine atoms on the board, and we're going to share electrons. Now, we cannot transfer electrons because one fluorine would get to its octet, but the other fluorine would be further away than it started. So instead, we're going to do this. Here's our sharing going on. There you go. Which electrons were shared? These two. They're between the 2 nuclei, the 2 Fs there. So those 2 electrons are shared and counted as if they were associated with both atoms at the same time. So now what I can do is I can say, okay, I'm going to search for octets. Do I have an octet? Yeah. And then for the other atom, do I have an octet? We're going to go this way, and then, oh, look what I'm doing here. Yeah, I do. So if you have a situation where you just don't have enough electrons, this works out for nonmetals. And in doing so, you attain an octet for multiple species when you just don't have enough electrons to normally do it. Okay. These electrons right here, these are my covalent bonding electrons. Co meaning communal, as in we're all sharing here, and then valent meaning valence electrons. So our goal is going to be to share electrons between 2 atoms using only the single electrons on each of them. And so there, we've counted our octet, so we're good there. All right. I don't know why my diagram didn't appear there. There we go. All right. Now, whenever you share electrons, writing it like this is a little bit awkward because we're just throwing dots everywhere. So the convention is to use this line right here. Here's my line. Anytime you have 2 electrons that are shared, you draw a line. If you share more than 2 electrons in different directions, you draw lines in different directions, or even in the same direction if you're sharing more than 2 electrons. So 2 electrons represents 1 line. Or other way around, actually. A line represents 2 electrons. Now, what about the pairs on the sides here? These are called non-bonding pairs. Non-bonding pairs just hang out. They are electrons and they repel other electrons, but they don't form bonds because if I tried to share them with an atom, my electrons would be repelled by their electrons because I already have 2. I can't pair them together any further if I've already got a pair. All of your atoms, when you're drawing your Lewis structures, are going to have bonds and non-bonding pairs. And there should be a certain number of each of them. Make sure that you draw all of them to ensure that you get your structure correct. Okay? The non-bonding pairs will just be whatever electrons were paired when you first drew the symbol. And the bonding electrons will be all the unpaired electrons that eventually get paired together as you create the bonds. All right. Now, when you have created all of your bonds around all of your atoms and finished the structure, it's important to note that you are, again, trying to follow the octet rule. So the number of electrons around each atom should be 8. That includes bonds. Make sure you get all the bonds and all the non-bonding electrons in your count. Now, are there any atoms that break this rule? Actually, there are tons of them, but we're really only going to run into one. Hydrogen is the exception. Hydrogen only needs 2 electrons. So if you have hydrogen in your structure, hydrogen comes with 1 electron on its own. It comes with 1 dot. You just connect that to some other unpaired electron and you make a bond with hydrogen. That's easy enough, and we'll see that in action in a little bit. All right, so now we know the gist of this. So what we're going to do is I'm going to do the first one of these, and then I'm going to have you try the other ones just to see if you can get the hang of it. We're going to do a very simplified method of drawing Lewis structures, and then on the next slide, we're going to learn how to do multiple bonds and make bigger structures all at once. So this is the simplified form. I'm going to take my chlorines, and I'm going to draw the number of valence electrons around chlorine. So that's 7, because it's in group 17. And then I have another chlorine. And then I need to share electrons so that I complete the octet for everything. So remember, only unpaired electrons can be shared. So what I'm going to do is I'm going to share these two. And in doing that, my structure then becomes that. And that's the Lewis structure for Cl2 with a bond in it. Now, does everything have an octet? Well, I can count around the left atom, and I have 6 dots and then a bond which counts as 2, so that's 8. Same thing on the right atom, 6 dots and a bond that counts as 2, that's 8. Remember, the bonds are shared, so you can count them as many times as you need to. All the atoms attached to the bond get to count those electrons as theirs. All right, so I've shown you Cl2. Do BRF, which is actually exactly the same. And then try and do CF4 and H2O. We'll go over the answers in just a bit. 1 or 2 more minutes, we'll go over the answers. All right, sorry about that. Maya came in and I immediately started talking to her for some reason, and I gave her a hug. She's sad and lonely. I didn't mean to do that. Oh, that's okay. We'll just do another structure here. Okay, so let's do Br and F here. So bromine is also in group 17, so it has 7 valence electrons. And then we got fluorine here, which also has 7. I am going to do this to share my electrons. And then we'll just translate that into a new structure where my shared electrons have a bond. And then I will fill in the dots afterward based on where they were in the original structure. And there's the answer for that one. Now, for CF4, for carbon, I have 4 valence electrons around it because it's in group 14. And then for fluorine, I have something like this. I just got a bunch of these. It's just a bunch of unpaired electrons on one side, and all the remainder are paired. So what I can do is I can sort of do like a little football diagram, but I'm not going to make a very good structure out of this. So I could bond these two, and then share these two, and then share these two over here. But now I need to tidy that up. So I need to make my actual structure have linear bonds in them. So I'm going to take my carbon, and I'm going to just put it in the middle. I'm going to go like this. Bond, 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 bond. And I'll put my F's around it. And then I got to fill in the non-bonding electrons. There were 3 pairs of 2 on each fluorine. And there you go. There's your structure. So this right here can be good for blueprinting. But you want your structure to look like these. These are your structures that we want. Now, with water, you're going to do something similar. I've kind of run out of room here. So let me clear the screen here. And we'll write down water here. So oxygen has 6 valence electrons because it's in group 16. And then hydrogen just has 1 valence electron because it's in group 1. And then I'll just connect these guys like so. That almost looks right, but let's straighten it out a little bit more. And there you go. I didn't check for octets on any of those, but you could do that if you'd like. You'll see that all of them have octets. So all the structures are good. That's the gist of drawing simple Lewis structures. We're going to draw ones that are slightly more complicated, but we're eventually going to get to the point where this like connect the dots method doesn't really work anymore because we just don't have the capacity to draw all of the dots and all of the lines in an intuitive way when there are too many options. Like, then we have to start guessing, and most ways don't work, and we need another method. So we're going to come up with another method in the next few slides. All right, so what happens if you want to make multiple bonds? Well, you can. There's no restraint on the number of bonds that you can make between two atoms. So, for instance, if I have oxygen, and I have two atoms that look like this, I could say, okay, well, I'm going to connect this one here. But what if I want to connect the other one too? Then I would make 2 bonds between the same 2 atoms. That's totally allowed. If I do that, that will mean my structure looks like this. Now, these electrons are the shared electrons, which we'll highlight. But remember, every time you have 2 electrons shared, you draw a line. Well, if I have 4 electrons shared, I should draw 2 lines. So, let's do that. There's my double bond right here. And the unpaired electrons are just carried along. You'll notice they're kind of at right angle, or kind of diagonals, I guess I would say. There's a specific reason for that, which we will talk about probably at the very end of today or on Tuesday. What is the absolute maximum number of bonds that you can make to something? Well, it turns out it's actually 3. So if I have something like this, and I want to make bonds to other things, these electrons are sort of constrained to whatever sides they're on. So I could make these guys share, and these share, and these share. But then this one, I would have to do something like this. You can't make a bond going all the way around like that. Bonds only go in straight lines. So there's no way for this one and this one to ever reach. So the maximum number of bonds you're allowed to make is 3. So that'd be a covalent double bond. A covalent triple bond is possible. So what I want you to try and do is draw the covalent triple bond, hint, that's what this is, for nitrogen gas. So N2. Draw the Lewis dot symbol for each nitrogen atom, and then try and draw the bonds, and see if you can find the triple bond in it. I'll give you 2 or 3 minutes to do that. All right, so hopefully you did something like this. So you draw nitrogen. Nitrogen has 5 valence electrons because it's in group 15. I need a second nitrogen. And you'll notice I'm purposely putting the paired electrons away from each other because they can never bond, right? The paired electrons just hang out. They're non-bonding. And so I would get these two to share, these two to share, and these two to share. And then we'll just tidy up. I shared 3 pairs of 2, so I will draw 3 lines. And there's the Lewis structure for nitrogen. Hopefully that's what you drew. All right, here's another example for you. I gotta clear this so that you can read the text here. I want you to draw both of these structures, C2H2 and C2H4. One of them has a double bond and one of them has a triple bond. Now, my recommendation for you is to evenly distribute the H's across the C's. So you're going to have something that looks like this. So it's C2, so you're going to have C, C, and then H's and H's. Draw all your dots and put all your pieces together. Connect in the H's and then see what's left over and see if you can figure out whether you make a double bond or a triple bond. So I'm going to give you about 4 minutes to do this one because you have 2 of them. But once you've drawn out all the pieces and put the H's on the sides that they probably should go on, connect the H's first, and then whatever's left over, see if you could share it. That'll get you the answer. All right. See you in a bit. I'll redraw the NN Lewis structure up at the top there, just so it's there on the screen. Let me know if you have any questions, though. One more minute, we'll go over the answers. All right, let's draw the Lewis structure. So I'm going to start with C2H2. And so my advice was to put the H's on the opposite sides and then just sort of see what else happens. So H always comes with 1 electron, and carbon always comes with 4. All right, so we're going to make these bonds over here. So, and then what else can I do? Well, I got to pair all the electrons together, right? So I'll share these and these and these. You'll notice that in all these structures that we're making, we always pair all of the non-bonded, or not non-bonded, all of the single electrons. The ones that are already paired, they just hang out. But if you have single electrons, they are always getting paired. So let's tidy this up. So I have triple bond here, and then single bond to my H's. So that's C2H2. It has the triple bond. Now let's try the other one. So I'm going to put 2 H's on each side here. But we're going to do the same thing that we did before. And so now I'm going to go, okay, well, I'm going to connect these two. It doesn't matter which two you pick. I'm going to pick these two. And then what's left over? Well, I'm going to pair those and those. So my structure would then look like that. So C2H4 has a double bond. Which is interesting because you might have thought, oh, well, if there's more H's, maybe there's more bonds. That's how you get the bond in the middle to be bigger. But it turns out it goes the other way. And you can't really predict that when you're starting out until you just draw the structure. So try not to guess what it is first. Just draw the structure, connect all the lonely unpaired electrons together to make bonds out of them, and see where you end up. There's the homework practice for this section, 5.1 through 516. So that will get you started on drawing Lewis structures. So in the next section, what we're going to do is we're going to use this ground sort of framework to make Lewis structures for any molecule we want to. However, we're not going to use the rules that we just established of draw the dots out and then connect the singles together, because that's going to give us too many options. So the molecules that I just gave you only had 2 types of elements in them, so it had C and H, for example. But I'm going to start giving you molecules with up to 3 elements in there, and it's going to be unclear, like, how do I arrange them without extra rules. So we're going to use these extra rules to follow this 5-step algorithm, but I think we might be almost due for a break here. Yeah, let's take our break now. It's a little early, I realize, but if I start this section, then we won't get a break until much later. So we're going to go take our break now. And that's for the previous class. Hold on, I got to clear that out here. All right. So I'll start the timer. I'll get the Zelda wave back on if I could find the music. There we go. and I'll see you in a little bit. Yay! We'll wind this down here. Alright, welcome back from the break. Hope everybody was able to top with their water, use the restroom, pet a cat, pet all the cats. I just wanted to hug every cat. However that meme goes, I don't remember. The video of the woman who says, I just love every cat. I want to hug them all, but I can't. If you haven't ever seen that auto-tuned, you should. It's amusing. Alright, so what we're going to do, now that you know the gist of how Lewis structure should look with all the unpaired electrons paired together as bonds and all the non-bonding pairs just hanging out on the sides and everything as an octet, we're going to devise this sort of algorithm to draw the Lewis structure for any molecule that you will be given. And so, that's you. I just want to hug every cat. Alright, so here's how this is going to work. I'm going to give you a molecule. We're going to do CO2 as our example here. And what we're going to do is we're going to first count some number of electrons around it, then create a structure, and then just start connecting and drawing in electrons following a very prescribed pattern, okay? Make sure that you follow these steps in the order that I present them to you, and that you don't go out of order. If you go out of order, then you hit issues, okay? The most important thing here also is counting. If you make a mistake in counting numbers, then you will always get the wrong answer. So if you mess up this first step, which is count how many electrons you have, you're going to have an issue. So I'm going to talk about the steps first real quick, and then we're going to go back over them one at a time and do CO2. So the first step is count your valence electrons. We did that for individual atoms on the periodic table. You could do that for a molecule just as easily. Like if a carbon gives you 4 and 2 oxygens each give you 6, there would be 16 total because you just add the numbers together. And you'll see that in a second. Once you know the number of electrons in your molecule that you have to work with, then the next step is to draw a sort of framework. The framework is like the skeleton or backbone of the molecule. You're going to put whatever atom is shown first in your molecule goes in the center. So for instance, if this was the molecule I was drawing, I would make a framework like this, where the first atom goes in the center. We'll call that the central atom. And then what I'm going to do is I'm going to connect all of my atoms together using electrons. Now, making bonds uses up electrons. So this total that we counted up here at the start, we're going to have X electrons available. We're going to have to deduct electrons for each time we use them for bonds and so on and so forth, okay? Once you have everything just basically hooked up, you're going to put electrons around the outer atoms first. So it says here around atoms bonded to the central atom. So this is just the outer atoms. Once you have given an octet to all of the outer atoms, you're going to then put anything left over on the central atom. And then finally, if you run out of electrons and you can't get an octet on the central atom, then you start making multiple bonds by moving electrons around. Now, that sounds really complicated sort of in theory, right? So those steps on their own aren't super helpful, but when we see a few of these examples, it'll all start falling into place. So we're going to go back to the first step here, and I'm going to give you a molecule. We're going to do CO2. Well, I mean, if I could capture the rules here. All right, so let's try CO2 first. So the first thing we want to do is we want to count the number of electrons in CO2. I don't know why I have that selected. There we go. If I was just drawing carbon by itself, I would have 4 valence electrons. So I'm going to write that. If I was going to draw oxygen by itself, I would have 6 valence electrons. But I have 2 of them, because it's CO2. So what I'm going to do is I'm going to total these together. So 6 times 2 is 12, plus 4 is 16. So that's counting all the electrons. That's the number of valence electrons that I have for bonding. Remember, we only want valence electrons, because valence electrons are the ones that participate in bonding. The other electrons don't do anything. They just hang out. All right, that's step 1. Once you have counted the number of electrons, now we can make our framework. I'm going to just truncate this part out because we don't need it there for this. So the framework is going to be based off of how our formula is written. The first atom is going to be the central atom. The exception is if the first atom listed is H. H can never be the central atom, because H can only bond to one thing. It only makes a bond to get 2 electrons, right? So let's draw our framework. I'm going to put the C in the middle, and I'm going to put the O's around the outside. You can put them wherever you want. It doesn't matter, as long as the C is between them somehow. Now I got to connect the atoms together. So I'm going to go connect, connect. Now, in order to do that, I had to make 2 bonds. 2 bonds is the same as 4 valence electrons, right? Because remember, each bond is 2 dots, and each dot is an electron. So I only have 16 to work with. I have already used 4 of them, so I'm going to deduct 4 electrons from my total. So I have 12 electrons now to play with. That was step 2. I have used 4 of my electrons to make bonds to hook up my framework. Step 3 is going to be make octets around all the outer atoms. So we're going to do that first. So I'm going to go just right up to this first atom over here on the left. I'm going to just give it an octet. Right now it only has this bond, so it only really has 2 electrons around it. So I'm going to go 3, 4, 5, 6, 7, 8. You'll notice I didn't do them one at a time this time, because we're going to fill them all in anyway, so I'm just going to go dot, 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 until I have paired everything together. So just draw on the pairs this time. That's very different than how we've been doing Lewis structures up until this point. But because we're sort of shortcutting for this special method, it's okay. How many dots did I put down? Well, I put down 3 pairs of 2. So that'd be 6. So I have to use those 6 out of my pool. So I only have 6 more. I'm going to do the same thing to the other outer electron, outer atom. That's this right here. 1, 2, 3, 4, 5, 6. Now that is an octet too, and I've used up all my electrons. So now the next step is, okay, are there any leftover electrons to put on the central atom? Well, no, I used up all my electrons. So step 4 is done. We'll go to step 5. If you run out of electrons for the central atom, make multiple bonds. So here I don't have an octet. I only have 2 bonds to my carbon, so I only have 4 electrons around it. I need to make multiple bonds. So what I'm going to do is I'm going to take a pair of electrons and sort of just put them in this region right here, so they're now between these 2 atoms as a new bond. So I'm going to start taking pairs of electrons to make bonds out of them. In order to do that, I have to erase them from where they are and then move them to their new location. When I do that, oxygen still has an octet, because I still have 1, 2, 3, 4, and then 2 bonds is 4 electrons, so that's 8. And this carbon over here now has 6 valence electrons, because it's got 3 bonds around it. How do I get it to an octet? Well, I do the same thing. I'm going to take these electrons over here and put them in this bond. You could take any of the pairs you want to. I'm just trying to make it symmetrical. Then we're going to erase this and put those electrons in their new home. Oop, there we go. Now I have an octet for everything. Because this oxygen has 1, 2, 3, 4 unpaired, and then 2 bonds right here, which are paired. They count as pairs because they're shared pairs. So that's 8 total. Same thing for this oxygen, 1, 2, 3, 4. Each bond is 2, so that's 8. And then this carbon has 4 pairs of bonded electrons for a total of 8. We can tidy up our structure if we really want to. But that would be the structure for CO2. Now notice how in the 5-step plan, we went from step 1 to 5, and we didn't go back and do steps or anything. You need to do the steps in the order that they come in, and if you skip a step because you couldn't do it, because like say you didn't have any electrons for it, you can't go back. You just keep going forward. It will all resolve itself at the end if you have done the steps correctly, and it works every time. The trick is just remembering the order of the steps. All right. So and then finally, if at any point you get to an octet for everything, you could just stop because no remaining steps will matter. By then you'll be out of electrons anyway. So these slides walk through how to do CO2. And you can see what we just did here, and there's our structure. So I'm going to give you a simple molecule here to try the structure on. You could totally do this with the connect the dots method, but what I want you to do is try and draw ammonia using the 5-step plan, okay? You may have to go back through the video because I can't actually get all 5 steps on the board at once. So I'll give you about 3 or 4 minutes to draw the Lewis structure of ammonia. Count all the valence electrons, that's step 1. Draw the framework, that's step 2. Outer octets is step 3. Inner octets is step 4. Make multiple bonds if necessary is step 5. Okay, good luck. I'll see you in a second. All right, one more minute. We'll go over the answer here. All right, let's go over the answer here. So, first step is to count the number of valence electrons. So, that would be, well, nitrogen looks like this. So, that's 5 electrons. Hydrogen looks like this. So, that's 1 electron. And there's 3 of them. So, that would be 5 plus 1 times 3, which is 8 electrons. Now, you don't have to draw the picture out every time. Eventually, you just start looking at the periodic table and going, oh, this is in group 5, so it must have 5 electrons. And that's what we're going to do from here on. So step number 1, count the number of valence electrons. Step number 2, I'm going to just draw the framework. So I'm just going to surround my N with H's here. And I'm going to start connecting them. Boop, boop, boop. I made 3 connections, 3 single bonds, so that's 6 electrons. So I need to deduct 6 electrons from our total. So I have 2 remaining electrons. That's step 2. Step 3 would be put electrons on outer atoms. Well, hydrogen, remember, it doesn't need electrons. It wouldn't make sense for me to do that because that hydrogen would have 4 electrons. It only needs 2 because it's hydrogen, yeah? So, step 3 is kind of a wash. Nothing happens. Step 4, put all the remaining electrons on the inner atom. We can do that. There's my remaining 2 electrons. We have used all the electrons. Does everything have an octet except hydrogen? Does every hydrogen have a duet? So hydrogen has 2 electrons. I didn't mean to actually accidentally tap the screen there. So this hydrogen has 2 electrons. This hydrogen has 2. This hydrogen has 2. And then does my nitrogen have 8? Well, it's got the 2 unpaired, or the 2 non-bonding electrons right here. And then 3 bonds is 6 total electrons, so 6 plus 2 is 8. There's an octet around nitrogen. Everything has an octet. This is the correct structure. Let's see if what I drew matches what's in the slide. And lo and behold, totally the same. Mine isn't at right angles that I drew. That's okay. We're not going to grade you on angles. In fact, you can't draw these structures into Canvas anyway. So you're going to have to draw your structure on paper and then report things about it in Canvas based on questions that it asks you. That was a really simple Lewis structure. I'm going to give you slightly more complex ones here. And so you could see that the number of atoms is going to increase, and you're going to end up with interesting situations. Now, I have modified some of these to give them charges. So you'll notice that on ClO and on NH4, there is a charge. What does a charge do to number of electrons? So for example, if I had carbon, it would have 4 valence electrons. But if I had carbon with a minus charge on it, that would be like giving it an extra electron, right? So with these charges over here, these are going to modify the total number of valence electrons. Think of the charges just kind of floating over the entire thing, because that's what it is. So somewhere in NH4, there is 1 fewer electron. So instead of counting the number of valence electrons you'd get from just adding the elements together, you would do that and then subtract 1 electron for that plus symbol. For ClO, you do the opposite. You would add all of the electrons from chlorine and oxygen together and then add 1 additional electron to the charge. So I'm going to give you... This will take longer, so I'm going to give you at least 5 minutes to do these. And then we'll talk about the answers when we get back. So I know it's not enough time yet, but what I think I'm going to do, so this is kind of a difficult subject. I'm going to write the answers on the screen, and then I'm going to let you keep working, and then we're going to go over the answers together, and we'll get to those answers from scratch. So I'm going to just do that quietly right now. So don't mind me. All right, I'm going to give 2 more minutes, and then we'll go over all the solutions. All right, let's go over the answers here. So you can see all the answers on the screen, but what I'm going to do is I'm going to go to this screen. There we go. I'm going to sort of hide the answers for now. We're going to just create them all from scratch so that you can see the process. But I did want to put the answers up there because I know for these questions in particular, while you're doing the exercises, a lot of people are like, did I do it right? And if you could see my answer, then you can work towards it. So if that helps you in any way, because I realize we're just getting started here. So let's look at CS2. So carbon has 4 electrons because it's in group 14. Sulfur has 6 electrons because it's in group 16. And there are 2 of them. So I'm going to add those together and I get 16. And you're going to be like, this looks a lot like CO2. And turns out, yeah, because oxygen and sulfur are in the same group. They have the same number of electrons, and in fact, they have the same structure. So when we go to make our blueprint here, everything's going to line up in more or less the same way as before. So step 2, I'm going to connect everything together. Then I'm going to do outer octets, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's all my electrons. But you'll notice I don't have an octet on carbon, so I need to move stuff over. So I'm going to take this guy and move it here. That actually looks really bad. Let me fix this. Oops. I'm going to take this guy and move it here. And there's the structure. It's all done. Hooray. And that should look just like what we drew on the board here, and it totally does. There it is up at the top. All right. With CH2O, the trick is, Oh, this is weird. There's a third type of atom. Does that change anything? No, do it exactly the same as you would normally. Put the first atom in the middle and then just put everything else around it. And it'll totally work. So let's count all the electrons. So carbon is still 4. Hydrogen is 1 each, but there are 2. And oxygen is 6. And I'll just add them all together. So 4 plus 2 plus 6 is 12. 12. And then we'll just do what I said. So H, H, O. Your O can go wherever you want to. It really doesn't matter. I'm going to connect everything together. And that took 6 electrons. So we'll do that. I don't really need to change the color, I guess. Now I need to put the remaining 6 electrons around my outer atoms. Well, H doesn't get any more because H only gets 2 total. So I'm going to put them around this oxygen. 1, 2, 3, 4, 5, 6. So that's all my electrons. I have nothing to put on the central atom for step 4, so we'll skip that. But step 5 is if you don't have an octet around the central atom, make multiple bonds. So I do need to do that because I only have 3 here. I need to get a 4th bond for 8 total electrons. We'll do that. And there's the structure. Do. All right, let's do the next one. So we got ammonium. So N is 5, H is 1, and there are 4 of them. And then this means lose an electron. Right? So I'm going to add these together. 5 plus 4 minus 1 is 8. And then when I draw my framework, you're going to see, oh, this kind of finishes itself really quickly, right? 2, 4, 6, 8. Oh, it's done. Ta-da! Now, something we didn't go over, but this is just convention, so you'll see this a lot. Whenever you have an ion, and so that's this right here, we got to indicate that on our structure. And so the way that you do that is you put your whole structure in brackets, and then you put the charge at the corner of that ion. And that's the correct way to draw this structure. Because we used up all 8 electrons in step 2. There's no reason to continue on the other steps because everything is used up. Everything has an octet. Everything's great. Let's do PCl3. Phosphorus is 5 electrons. Chlorine is 7 electrons, but there are 3 of them. So I'm going to add these together. 7 times 3 is 21. Plus 5 is 26. Again, be careful that you're doing the math right. If you miscount your electrons, your structure will be in shambles. So be real careful that you don't make a mistake counting. Step 2, let's do the framework. That was 6 electrons. Step 3, outer octet. So I'm going to go 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons to give everyone an outer octet. Now in this case, I have leftover electrons for step 4, so I'm going to put them right on the central atom. And then once I've done that, there's no need for step 5 because everything has an octet, so we're all set here. Ta-da! Boom. And then I ran out of space here, so can I go higher up? No, I used up the whole canvas here. So you can pause the video if you still need that. I'm gonna hit clear, boop, and we'll do the last one, ClO here. Well, ClO minus here. So I got chlorine, which is 7, oxygen, which is 6, and I got this, which is gain an additional electron. So 7 plus 6 is 13, plus 1 is 14. That's kind of a little off the screen, isn't it? Let me just do that. There you go. Cl is the central atom, but there's only one thing connected to it, so we'll just do that. And then outer electrons first. So we're going to do this atom first. And then we'll do the central atom, which was chlorine. And you're all set. Don't forget to put the brackets and the charge. All right, that's it for Lewis structures. Any questions, let me know. All right. The next section is for polyatomic ions. We're not... oh, and then there's the homework practice down here, so make sure we note that. How much time do I have left here? I only have like 12 minutes, so... Can't do geometry. What we'll do is I'm going to show you some of these Lewis structures here. For polyatomic ions, we'll do like one or two more examples, and I'll just have you draw the polyatomic ion part. So the point of this section is to show that even though polyatomic ions are ionic, the polyatomic part of the substance actually has covalent bonds. Now, whenever you have both bonds present, so you have both ionic and covalent bonds, only covalent bonds get solid lines. So never draw ionic bonds with a solid line. Ionic bonds are just you put the charges next to each other, and it's implied there. We already talked about how a positive charge influences the number of valence electrons you have, and the negative also does that too. So what we're going to do is we're going to draw the Lewis structure for this compound right here, Na2SO4. And so the way that this works is we first need to break this into the ions that are present. So you need to find the polyatomic ion, which is on that sheet at the beginning of Unit 4. And so what this is so I've got this ion, and I've got these ions. This is the polyatomic ion, and so now what I'm going to do is I'm going to draw the Lewis structure of that thing. And we'll do it just like we did in the previous section. So sulfur gives you 6. Oxygen also gives you 6. There are 4 of them. And then the -2 here is an extra 2 electrons. So this would be 24 plus 6 is 30 plus 2 is 32 electrons. That's a lot of electrons. And then we'll draw our blueprint. We'll connect them all together. So that would be 8. And then I'm going to put electrons around the outer atoms. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. That's all of them. So we can then put it around, put brackets around it, and put the charge in the corner, and we're all set. So that's the sulfate part. And then for the other atoms over here for the sodium, or the other ions, I should say, you just kind of attach them on the side. So that's what you would draw. So the important part of this is drawing the Lewis structure of the polyatomic ion, which does mean you have to go look up its charge if you haven't committed it to memory, which it's an online class. I don't expect that you would do that. So refer to the very first slide in Unit 4 for the polyatomic ions, and draw the Lewis structure of the polyatomic ion that you find, and then just attach the other ions, the cations, to the side like I did there. All right, so I'm going to give you, and it should look like what I just drew. So I'm going to give you a bunch of these here, and the homework practice for this. So this will be the last thing we do today. So I want you to draw the polyatomic ions. I'm actually going to highlight the polyatomic ions here for you. so that you can look those up. I want you to go find the charge so that you draw the correct Lewis structure. And I'll give you a hint. Whenever you're counting your valence electrons, you should always land on an even number. So if you landed on an odd number, it's probably because the charge you looked up was incorrect. So if you did Cn, like say 2 minus, you get an odd number. So that's an error, and you want to make sure that you double check that. Okay. I'll give you about 5 or 6 minutes to try these. We'll go over them together, and then we'll call it a day. 1 or 2 more minutes, and we'll go over the answers here. All right, let's go over these answers. So we'll do this. Oops, we gotta get rid of that. Goodbye. We'll scroll up to the top. So we want the nitrate part of KNO3. That is... I have the wrong color selected. This... Each nitrogen is 5 electrons, each oxygen is 6 electrons. 3 of those. And then I have this minus charge, which is an additional electron. Add them all together, we get 6 times 3 is 18, plus 5 plus 1, 24. Then we'll do our framework. 1, 2, 3 bonds, so that's 6 electrons. And then I'll drop the last 18 in around the outside as octets. That's 12, 13, 14, 15, 16, 17, 18. That's all of the electrons. I don't have an octet around the center, though, so I need to make a double bond. I'm just going to pick 2 arbitrarily and make a double bond, and it's done. Does it matter which one you pick? Nope, because you can rotate the structure. It's fine. In other classes, you'd learn that there's a little bit more nuance to this, but for our purposes, this is good enough. So that'd be nitrate. If we do carbonate over here, you'll notice that you're going to get more or less the same situation because this is 4. This is 6 times 3. And then you get the 2 over here for this guy. You get 24 again. And when you draw the Lewis structure out, you get the same result. So there's 6. Oops. So we'll do that, and then I'll just put the 18 around the sides. It turns out if you have the same number of valence electrons, you get the same structure every time. And then I'll just do this, and it's done. And then don't forget the barium over here. Then we get sodium azide, so sodium is plus like that. Azide is minus. There are 3 nitrogens, and then I gotta add this in here, so don't forget that. That's 16. Which N is the central atom? Well, it doesn't really matter. Just put them all in a line, right? So 2, 4, 5, 6, 7, 8, 9, 10. Wait, hold on. Sorry, I got confused. 2, 4, 6, 8, 10, 12. There we go. So that's all of them. All right. I don't have enough electrons for the central atom, and it needs electrons, so I'm going to move some over here, kind of like with CO2. And there we go. We'll put the brackets around it, put my charge around it, put the sodium around it. You're all set. And then last one, KCN. I'm out of time here, so I'm just going to do this real quick. So that's 10, C, N, 2, 4, 6, 8, 10. So there's all 10 of my electrons. I need to make more bonds to this carbon, so I'm going to take one here, boop, and one here, boop. Now everything has an octet. And there you go. There's the structure. All right. So hopefully by now you're proficient at drawing Lewis structures, since that's almost what we spend the entire period doing. There's the homework practice for that section. Do as many Lewis structures as you can, because when we come back tomorrow for tomorrow's lecture, remember there is a lecture tomorrow. We're going to talk about geometry and how all of these things are oriented in space. And in order to do geometry, we need to be able to draw the Lewis structure. So do as much practice as you can. But that's going to be it for me today. I hope you have a wonderful rest of your afternoon. I would say go out and see the sun, but it got really cloudy all of a sudden. So just take it easy. Make sure you get those assignments turned in. Quiz number 4 is due tomorrow. Lab worksheet number 2 is due Wednesday. There's a lot coming up. Make sure you stay on top of it. Have a wonderful rest of your day, and I'll see you tomorrow.